Hi, welcome to another lecture of Physics 2101. We're going to be continuing today where we left off, which is chapter 9. In the previous lecture we did chapters 9.1 to 9.3, and towards the end of it we defined linear momentum and we defined the force, or a force, to be a change or the rate of change in momentum. And we said we know this in multiple ways from everyday life, we just don't realize that we know it per se. So today we are going to be taking a bit more of a look on center of mass, how it works, and linear momentum. Okay, let's get started. Okay, this is something that we used to play a lot when we were children. Someone throws us a ball and we catch it. Now there are two ways to catch it, and if you are a fan of basketball or baseball or cricket, you will notice something, that when professional players who do this day in and day out try to catch a ball, they never just go, "I caught it." Rather, they usually use both hands or one hand to catch the ball and then start going a bit backwards, as if they are slowing it down gradually. And I used to think that was just a technique, but it turns out that technique has a very valid physics reason, and that reason is what we're going to be discussing today. So let's take a look at this guy who has an incoming red ball. He catches it and then he pulls his hand backwards. What is it that's going on here? Well, the ball weighs about 200 grams. It has an initial velocity of about 10 meters per second, which is quite fast. And towards the end, it also has 200 gram mass. That hasn't changed, but now it has zero velocity. So all of that energy, half mv squared, needs to go somewhere. But back to that in a second. Now we have two options. Option one, we can reduce this velocity from 10 to 0 in 1 second, which is what we do if we immediately catch it like this. Or we can do it gradually over a delta t of 10 seconds. What's the difference between the two approaches? Well, we define the force as the rate of change of momentum. So before we go into a whole load of maths, okay, if I stop it quicker, then delta t at the bottom of this equation is smaller, which means my f is going to be big, and vice versa. But how does it work out mathematically? Well, let's rearrange this a bit. I'm going to be taking dt all the way up to f net. So now I have dp equals f of t dt. I've changed it into a pesky integral rather than a nice differential. But it still says the same thing. What does this say now? It says if I take my force over the duration that it acts on, I get my change in momentum. So far so good. Now let's take a look at this photo. And particularly, let's look at this area that is between the ball and the bat. Okay, this area between the ball and the bat has caused the ball to deform. If you take a look, there's a slight curvature over there. Yeah, the ball is being deformed. What is happening here? Well, let's take a look in a schematic way. Here's the bat in brown, and here's the ball. Now we have an f of t that is acting on the ball, and my rate of change of momentum, if I want to know my total rate, and I have dp, I will integrate it over all of time, and I will do the same for f of t d of t. And what I get is, on the left hand side I get delta p, my net change in momentum, and on the right hand side what I get is, we call this impulse. Okay, What is impulse? Impulse, which we use a capital letter J for, and it's a vector, is defined as, I have to thank the student who sent me feedback and informed me that sometimes my photo actually blocks the view. Okay, so impulse J is defined as the integral of the force over the entire time it is acting on it. What's another way to say this? Well, a simpler way just to have a nice and neat equation. PF minus PI, final momentum minus initial momentum, the difference is J, impulse. Let's take a look at a PIQ. Ball bouncing from a vertical wall. A ball of mass m moves to the right with constant speed v. It bounces to the left, and now I need to change this back down here. It bounces to the left from a vertical wall with the same speed v. So it's going into a wall, into a wall, into a wall with speed v. Boom, and then it goes again with speed v in the opposite direction. What is the change, delta px, in the ball's linear momentum? I'll stay silent for a few seconds. I recommend you pause the video, try to do it yourself, and then come back and watch the rest of the video. Alright, what is the change? Well, you have your final momentum, which is going in that direction, and your initial momentum is going in that direction. But then you have a minus sign in between, so at some point you're going to have maybe minus minus, depending on whether you decided that going to the right was positive or negative. I'll leave it to you to figure out. So, we still haven't answered, we have said a lot of things, we have defined impulse, but we still haven't answered our main question. What is the difference between stopping that ball within 10 seconds or within 1 second? Well, let's draw the impulse, otherwise known as, let's draw a curve of the amount of force with the time. Now, this first curve is the amount of force in some amount of time, delta t. Okay, you can see that the force very quickly increases and then very quickly decreases. Now, I can instead spread out this force, have it at a much lower value, only a longer amount of time. Just like with velocity and speed, different velocities and different speeds over a large amount of time, we could find average velocity or average speed. Now we can find average force. And the average force will give me the exact same area under the curve as I have with the actual force distribution. Now this is the difference. Okay? This is the difference. How much is the average force that professional sports person's arm or hand gets on a constant basis? Now, if you play this once in a while with your brothers or with your sisters at home, it might not make a big of a difference. But if you're playing professionally and those people throw the ball really, really fast, then it will make a difference in the long term, whether you have shoulder injuries or not. Let's do a practical example. Here is a car that is going towards a wall at an angle of 30 degrees. And it weighs 80 kilograms, or the person in it weighs 80 kilograms at least. And it's going with a velocity of 70 meters per second. It then hits the wall, deflects, it's now away at an angle of 10 degrees, and its final velocity is 50 meters per second. What is the impulse on the driver due to the collision? The impulse is the rate of change of momentum, is the change of momentum, Pf minus Pi, So I need to find out what is my PF and what is my PI. The directions, the angles, take all of that into consideration. And that's of course MVF minus MVI. This will be our X component, and we will have our Y component. We will separate them into Y and X components, just like we do for velocity, just like we do for acceleration, etc. It's the same thing. And we will end up with J being minus 910I minus 3500J, kilograms meters per second. Now that might not really tell us much. Okay, 3500 sounds like a big number, but I really don't know what the point of this is. Well, let's translate it. First thing first, what's the modulus? The modulus of this is about 3,600 kilograms meters per second. And the impulse on the car is equal to the change in momentum. We figured that bit out. Angle, jy over jx, it's a normal vector, 75.4 degrees. We know what j is. This is all fine, but now the question is, the collision lasts for 14 milliseconds. Car accidents are usually very, very quick. Okay? What is the magnitude of the average force on the driver during the collision? Now this is where impulse is important. This is where that 3600 comes into an idea. We said force is what? J over delta t, right? Now you put that J in, and you put that delta t 0.014, 14 milliseconds in, and you get a whopping large number. 2.6 times 10 to the power 5 newtons on the body of that driver. This is huge. Let's look at another PIQ. A ball bouncing from a horizontal wall. We have a figure showing an overhead view of a ball bouncing from a horizontal wall without any change in speed. So the velocity changes, the direction changes, but that's about it. What is the change? Delta px in the ball's linear momentum. What is the change delta py? And what's the direction of the change of momentum? I'll again leave it on the screen for a few seconds before moving on. Okay. We defined linear momentum, we saw how it works. Now, how does it help us in general? Well, one thing is to figure out what happened in car crashes and how to catch a ball the correct way around, but what else? We have an idea. We spoke before about conservation of energy. Yeah, we said that energy can be moved between things, it cannot be created, it cannot be destroyed, etc., etc. Let's look at the same idea in terms of momentum. My force is the rate of change of momentum. This much we know. Now, what happens if all of my forces are internal? My net external force is 0. What does that mean? If a system is isolated, then the rate of change of momentum due to an external force is exactly 0. And if dp by dt is 0, it means that the initial momentum equals the final momentum. Why is that useful? How can we use it? Well, if we take this definition that p is equal to constant for a closed isolated system, and we declare this to be a law of conservation of linear momentum, then we can have some very interesting results. Let's take the first result, a rocket. A rocket is in outer space, it's doing nothing, it's just standing like this. Velocity 0, p equals mv, momentum 0. Good enough? Now how does it move? It cannot hold onto anything, it's in vacuum, it's in space. So what does it do? It starts thrusting gas from the backside. Now that gas is moving at a velocity, p is equal to mv. But because it's an isolated system, it's not interacting with anything, and this gas pressure is coming from the inside, it means my total momentum still needs to be 0. So if I have minus mv in this direction, then my only way of having a total of 0 is to also have a plus mv in this direction. And this is exactly what we see. The gas is going backwards, and the rocket is going forwards. We define the entire system as a rocket plus its gas. There are no internal forces. In this case, it's very clear that there are no internal forces because, well, the gas is coming from inside the rocket. So, sorry, there are no external forces. So my external force is 0, P is conserved, P rocket equals minus P gas. Let's look at 2 PIQs. 1. A man standing at rest on a horizontal frictionless floor might get himself moving by what? Walking, rolling, exhaling vertically, crawling slowly, or throwing a shoe horizontally. Think about it. Horizontal, and there is no friction, which means, unlike on Earth, normally when we want to move, we push on something with our foot and we move. But if there's no friction, we cannot push. It's like one of those really funny internet videos where someone's trying to run, or in cartoons like Tom and Jerry, when they have an oil slick and they're trying to run and they're just going nowhere but just moving at the same place. Think about it. I would say walking is not possible because there's no friction. Rolling is also not possible because the person would just roll in the same place over and over again, not going anywhere. Exhaling vertically wouldn't help because although that's going to give you a net change in momentum, there's still gravity downwards, so you're not going to do anything. Crawling slowly isn't going to work either, no friction. The only option is throwing a shoe horizontally. It's just like the rocket. The shoe is going to have a momentum mv in that direction, which means you're going to get an mv in that direction. Another PIQ, Salim, who weighs 45 kilograms, runs and jumps horizontally off a stationary 168 kilogram boat. Now Salim's velocity as he jumps is plus 2.7 meters per second. If we ignore friction and loss of energies, what is the velocity of the boat? That I'm not going to do. I'm going to leave you to do on your own. Okay, who here is a fan of billiards or snooker? Or at least know it? This is your typical billiard/snooker table. And what I'm going to play now is something that we see over and over again. Ball coming, hitting something, the first ball stopped, the second ball moved and then stopped. Very well. Now this very simple interaction has a lot of physics behind it. How? Let's bring together two concepts that we have been dealing with independently so far. Momentum and kinetic energy. And let's bring them together. How? Say, for example, you have this cube and this ball, and they hit each other. What happens when they hit each other? Well, we have three main options. There are sub-options after them, but the options available in the first place are only three. Well, first thing first, we know that momentum is conserved because this is an isolated system. There are no external forces. This thing was moving, this thing was moving. We don't care how they started moving, they're both moving. And then when they hit each other, this is an internal force. After collision, we have three options before we discuss these. Well, one thing that could happen is this ball hits this ball, and then both of them are moving in different directions. One of them increases velocity, one of them decreases velocity. Another option is that one hits the other, it stops, and the other one keeps moving, like we saw in the video. A third option is, like in really, really bad car crashes, you would get one hit the other, they become one object and start moving all together, as if they have always been one. What's the difference between these three cases? Well, one is called elastic, in which kinetic energy is conserved. One is called inelastic, where some kinetic energy is not conserved. And then we have a special case, which we call completely inelastic, in which after the collision, the objects just stick to each other like a really, really bad car accident. What's the difference? We will start with inelastic collisions first. Okay, let's look at a one-dimensional inelastic collision. We know Pi equals Pf. Here's two bodies. Body 1, M1 is moving with V1. Body 2, M2 is moving with V2. This is before. Then they hit each other. After they hit each other, they are both still moving in the same direction. They both still have the same masses, only their velocities have changed. Now this has V1F and the other one has V2F. How do we calculate the final velocities? Well, we know Pi equals Pf. Let's write it down. P1i plus P2i equals P1f plus P2f. Now let's expand it. M1 V1i plus M2 V2i equals M1 V1f plus M2 V2f. So far so good? Let's go back to this. Hit. This time they're both moving together as one. This is another option. In this case, we had an M1 V1, but M2 had V0, no moving. Afterwards, we have one mass together, M1 plus M2, and one V. Okay? We no longer have two objects, we just have one object. How do you write this one now? Well, before we had M1 V1 plus M2 V2. Now I know you might be asking, okay, but this doesn't say this way. Well, let's not take any shortcuts, and let's do it. How do I get out of this? There we go. Let's do it in detail. I will write M1 V1 plus M2 V2 I equals M1 V1F plus M2 V2F. We always start with this. Any other law is a special case of this. Do not try to memorize 60,000 different special laws. Know this law, the original one, and then you can derive any other from this. Okay. Now, M1 is okay, V1 is okay, M2 is okay, but V2 was 0 because the ball was not moving. Right? Okay. Now here, M1 is still okay, M2 is still okay, V1F is still fine, V2F is the same as V1F because they are moving together. So now we write it together. We write it again. M1 V1I equals M1 V1F plus M2 V1F, which is the same as writing M1 plus M2 V1F. Okay, and if we take a look at this is exactly what we have written. Yeah? Okay. What do we do with these? Let's take a look at one final thing. We still have these two balls. What's going on? That red dot in the middle that you're seeing, that is the center of mass, which we rambled on and on about in the previous lecture. Now take a look at how fast the center of mass is moving. It's moving. Now yes, first the number 5 ball was moving, number 4 was not moving, then number 4 was moving, number 5 was not moving, but the center of mass keeps moving at the exact same rate. It doesn't speed up, it doesn't slow down, nothing happens. It's as if nothing is happening actually. Why? Well, our F net external is 0, correct? So F equals ma. But if F equals 0, then A is equal to what? 0 has to be equal to 0, and the total mass is not 0. So the only thing that's possible to be 0 is acceleration. We can take this as a rule, and we'll do that right now. Here's the velocity of the center of mass. We have an incoming projectile in blue, and we have a stationary target, and that thing is coming in and it hits it. Okay, our stationary target is the white ball on the axis. Pink is simply the center of mass. There's collision, and then they both move together. And we would notice that the COM moves at the same velocity even after the bodies stick together. And so we can take a general rule to make it easier for us, that momentum is the total mass times the velocity of the center of mass. So if I have the center of mass and I know what's my velocity of the center of mass, then the momentum of that system is simply the total masses multiplied by that velocity. What do I do with this information? Well, first let's do a whole bunch of maths. P equals mv com. P is equal to P1i plus P2i plus how many P's we have. And capital M is M1 plus M2. Now this gives us a back root. If we don't know what Vcom is, we can find it if we know the total momentum and the total masses. We can do Vcom equals sum of the momentas over sum of the masses. Why is that useful? Well, say you want, and this is an actual example, it's also in your book, sample problem 9.07, but it's also a real world case. Now, before we had some really fast cameras, people wanted to know how fast a bullet is going, but they didn't have fast enough cameras to record it and slow it down and measure. So what was another way they could do? They had this idea, what if I shoot a bullet at a piece of wood that's just hanging? Okay, it's not moving, so kinetic energy is 0. And momentum is 0. And then once the bullet goes inside, this thing is going to move and it's going to go up. And using that bit of information, we can reverse engineer and calculate what was the velocity of the bullet. So they tried it. Okay, mass of the wood is 5.4 kilograms. Mass of a bullet is on average about 9.5 grams for a small pistol. Okay, now what's the speed of the bullet just prior to the collision? Now after the collision, what's going to happen? This thing is going to move a bit and it's going to increase its height by about h. Once they did that experiment, they found that h, that increase, was about 6.3 centimeters. And now they had all the information they needed to do the calculation. Total momentum before the collision equals total momentum after the collision, and they use our equation, and what do they end up with? Well, a whole bunch of maths. Let's take a look. M1 V1 plus M2 V2 equals M1 V1F plus M2 V2F. But our final velocities are the same because the bullet goes inside the wood and doesn't come out. So we get our equation up in the corner here. V equals M1 over M1 plus M2 V1I. Now I can rearrange this whole thing. Okay, but I'm not going to do that. We keep that momentum. But then let's look at energy. Okay, initially we had kinetic energy. At the end we only have potential energy. So half mv squared on the left hand side is equal to mgh on the right hand side. So V equals, we solve for all of that and we end up with V equals something. Now since we're not in a lecture hall, I can't do this on a board, and doing this on a virtual whiteboard without interaction is not very useful. But what I am going to suggest you do is, please try to do this problem on your own and see how it works out. Okay. Now if we put in all the numbers, we get that the initial velocity of the bullet is 630 meters per second, which turns out to be quite accurate. It's amazing how much information we can get from very, very simple physics. So the last two things we're going to do is show a PIQ here. I'll give you a minute. And another one. And with that, we actually end today's lecture. Now, what I suggest you do is go through these PIQs, go through the questions as needed, and after that, you can email, you can come to the office hour, virtual office hour, or we can discuss however you see fit if you have any problems. As usual, feedback is welcome. I hope this was useful. Have a good day.